Okay, I just realized that. Okay, I hope that works now. Okay. So the model that we're going to study is the Einstein scalar field system with negative cosmological constant. So the Einstein equations are Ricci curvature minus 1/2 scalar curvature times the metric plus lambda times the metric. And on the right-hand side, you have the energy momentum tensor of the scalar field. And the equations for matter, this is the wave equation for the scalar field. So we're going to study this system in symmetry. Namely, we'll work in the class of circularly symmetric solutions. So for these, you always have global double null coordinates u and v, with respect to which the metric takes this form. So it's minus omega squared du dv plus r squared d theta squared. And everything, so the laps, r and phi, are all functions of u and v. Okay, so this is the symmetry class that we're working in. And this model was actually first studied in the numerical relativity literature. So this is work of Pretorius and Chaptuik that I'll talk about more very soon. But let me first tell you what is the motivation sort of for considering this system. So the point is that this is actually the simplest system in 2+1 dimensions for which you have dynamical formation of singularities. So to see this, let me just go back to the equations. So first of all, if there is no scalar field, as you would expect, you have some kind of a Birkhoff theorem, and there's rigidity, and okay, so there's no non-trivial dynamics. But interestingly, is that in 2+1 dimensions, if there's no cosmological constant, but you have a scalar field, then you actually cannot get dynamical formation of singularities. So you really need to look at this model to have sort of non-trivial dynamics. And at all times, you should compare sort of what I'm saying with the 3+1 dimensional Einstein scalar field system in spherical symmetry with no cosmological constant. So keep in mind that in 3+1 dimensions, so this model was introduced by Christodoulou in the 70s, and there's a lot of work done in this model. But in 3+1 dimensions, this is, again, the simplest model for which you have non-trivial dynamics. Yes?
Can you say quickly why does the cosmological constant? What's the abstraction?
So somehow, well, I'm not actually going to show you the equations, so I can't really show you. But basically, what happens? Oh, I'm going backwards. Okay. So what happens is that when there is no cosmological constant, R actually is just the Minkowski R. So then the wave equation is just the wave equation of Minkowski, and okay, you can basically not get dynamical properties. No.
And is it important that it is negative?
Yeah, I think that then you have a very different flavor of the problem. Yeah. So yeah. Okay. Okay, good. And now, let me talk a bit more about this, about the model. And of course, since we have a negative cosmological constant, the natural problem to consider is an initial boundary value problem. And we're going to have reflective boundary conditions at null infinity. And null infinity, again, is the negative cosmological constant case. So null infinity is going to be a time-like boundary. And moreover, we're actually only going to study solutions which arise in gravitational collapse. Right? So these are solutions which have a regular center gamma at r equals 0. So everything that I'm talking about is like one-ended with a regular center. Okay, this is our setup. And you can actually classify all the solutions that arise in gravitational collapse for these equations based on their global properties. So you can classify this as follows. So you can have non-collapsing spacetimes. So these are spacetimes that don't form singularities. You can have black hole spacetimes. And then you can have naked singularity spacetimes. So I think that all these names are sort of pretty intuitive, but I'll now go into detail and explain, define this precisely and explain some more of their properties. So first of all, non-collapsing spacetimes. So these are spacetimes which have the following Penrose diagram. And let me just draw this here because I'll want to refer to it later. So in this case, I have my center gamma, which extends all the way to little I plus. And this is my null infinity. And again, this arises from data on an outgoing cone C0 plus. So these are non-collapsing spacetimes. And in this case, as you can see, you don't form any singularities. And moreover, you basically have that both null infinity and the center gamma are future complete. Okay, so this is what I mean by non-collapsing. And you, of course, know an example of such a spacetime. And this is the ADS solution in 2+1 dimension. So I gave you the formula here. in I guess static coordinates, and of course in ADS the scalar field is vanishes identical. Okay, so these are non-collapsing spaces. Okay, then moving on, we have black hole spacetimes, and first I'll talk about a bit about the BTZ family. So this is one parameter family of circularly symmetric static black hole spacetimes, and I'm giving you the formula here. Again, the scalar field vanishes identically, and okay, so more generally, you could consider this family for all values of parameter m, but somehow it turns out that these are actually black hole spacetimes only when m is greater than 1. Okay, and however, those sort of analogously to, let's say, Schwarzschild or Schwarzschild ADS, so the BTZ black hole spacetimes do not arise in gravitational collapse. Okay, so these will be like two-ended, and we only care about things that arise in gravitational collapse. But however, they play a very important role sort of in understanding the solutions near null infinity. Okay, so they still play a fundamental role even if they don't actually arise. Okay, so then the actual black hole spacetimes that arise in gravitational collapse can have the following two Penrose diagrams. So I'm representing them here, and you see there are two possibilities. So first of all, on the left, I have a black hole spacetime which has a space-like only singularity. So this is this cal B, which is space-like. And again, let me draw this because I want to refer to this later. So I form a singularity at the center, which I'll call B gamma. And then I have a space-like only singularity. Then this goes to little I plus. Okay, and then this is my horizon. Okay, so in this case, the singularity is space-like only. But then we have this other option in which I say that I have a black hole spacetime with a locally naked singularity. So by locally naked singularity, I mean that I have a null piece, which I denote by B naught, which arises out of the first singularity at the center, B gamma. Okay, so that's what I mean by having a locally naked singularity. And again, I'll also draw this here. So I have a null piece, that's my locally naked singularity. And then, okay, this has to become space-like, gets to I plus. Okay, and what you can actually show, let me just again go here, is that actually black hole spacetimes have a future complete null infinity. Okay, so finally, you can have naked singularity spacetimes. So in this case, I have again a first singularity at the center B gamma, and then I have a null piece B naught arising out of it, but this actually extends all the way to I plus. Right? So in this case, there is no black hole. There's no black hole region. And finally, I'll draw this here. This is the last thing that I need. So this is a naked singularity spacetime. Okay, and sort of the intuition is that you see, I have now a singularity B gamma, which is not hidden behind an event horizon. So this is visible to observers that are far away, and this is why these are called naked singularities. And also, I want to make, though, a remark about sort of different definition of naked singularity spacetimes, which is also very common in the literature, and say that if null infinity is future incomplete, you get that the spacetime has this Penrose diagram, so it is a naked singularity spacetime. But the definition of naked singularity spacetime that I have is a bit more broad, and I really want to allow any spacetime that has this Penrose diagram. So in particular, I can also allow spacetimes that have this Penrose diagram and have a complete null infinity. Okay? Okay, so now having introduced all these, there are some very natural questions that you would like to ask about naked singularity spacetimes. So the first question, it's very reasonable to ask if there even exist examples of naked singularity spacetimes. Okay, so we have example of non-collapsing spacetimes, ADS, and it's not too hard to construct examples of black hole spacetimes. Okay, these are not the BTZ ones, but you can construct something that arises in gravitational collapse, but it's usually much, much harder to construct examples of naked singularity spacetimes. And then the second question that you'd like to ask is strictly harder, and you ask if there exist examples of naked singularities which moreover arise on the threshold of non-collapse and black hole formation. Okay, so these would be negative singularities that are unstable both to non-collapse and to black hole formation. And why are you asking this? Well, as we just heard earlier today, these are very much motivated by numerical relativity works on critical collapse. And while this question is strictly harder than the first one, it also kind of tells you a way of where to find these and how to look for them, because you'd like to find them, as they arise in critical collapse. Okay, so these first two questions are about sort of existence of, and constructing examples of naked singularities. But then you would also like to ask the question of how common naked singularities are, right? Because these have singularity that is not inside of a black hole. They're supposed to be quite pathological. So the question that you're asking is if these, if naked singularity spacetimes are non-generic. So this is a statement of the weak cosmic censorship conjecture of Penrose, which of course, in its full generality is completely open. It's one of the main open problems that we have. And I'll talk about this problem in symmetry. Okay, and finally, this question is more of an open-ended question, is that you'd like to understand in detail what is the structure of the moduli space of initial data. Okay, so let me be a bit more precise though what I mean by this, and state what I'll call the critical collapse conjecture. So this is, again, a conjecture that's very much inspired by the numerical relativity works on critical collapse, and it conjectures that the infinite dimensional moduli space of spacetimes looks as follows. So I have black hole spacetimes, I have non-collapsing spacetimes, and these are separated by a codimension 1 threshold, which consists of naked singularity spacetimes. Okay? And then I can also have naked singularities out here, which are not non-threshold. Okay. So this is, the conjecture that you would like to prove, and we're nowhere close to proving such a conjecture. However, this is the source of, this can be the source of many open problems to work on. And yeah, let me just say that basically rigorously, there are no results. There are very, very few results in this direction. However, for matter models which allow for matter models which allow for extremal black holes, actually many aspects of this picture have been understood. For example, in recent work of Angelopoulos, Kelle, and Unger, which you might have heard about last week. But in the case of matter models with scalar fields, where you have no external black holes, so it's really only naked singularities that could occur, we know very, very little from this. Okay, so then let me tell you about what's actually being done, and I'll start with for the three questions that I asked before, and I'll start with work in 3+1 dimensions. So first of all, on the question of constructing examples of naked singularities, there's famous work of Christodoulou from '94, who constructed the example for the spherically symmetric Einstein scalar field system. Okay, and then much more recently, there's work of Rodniansky, Schlappen, and Rothman in '23, who constructed actually examples of naked singularities for the Einstein vacuum equations. So notably, right, if you work with Einstein vacuum equations, it means you're not working in spherical symmetry. So you have to do a lot more to construct such examples. But something interesting that I want to point out about both of these constructions is that their examples actually arise from initial data which is of low regularity. Okay? So the data that leads to these examples is not actually smooth. So these are the examples that I'm mentioning just for naked singularities. And then moving on to the question of naked singularities which are on the threshold of non-collapsing black hole formation. Well, basically, all we have are numerical results examples. So this started with in spherical symmetry with the work of Chuktuik in '93. And okay, there's been a lot of results in this direction since, but somehow these are much, much harder to construct rigorously. And, these would arise by the nature of sort of how critical collapse work. This would arise from smooth initial data, but somehow these are very hard to construct, and yeah, we're nowhere near doing this rigorously. Okay, and then moving on to the question of cosmic censorship. So actually, this has been done by very well-known work of Christodoulou in '99, again for the spherically symmetric Einstein scalar field system. And let me though point out that it is essential in his proof that he works in a low regularity class of solutions. So this somehow seems to be a theme both in the examples and in the proof of cosmic censorship. And again, this is really essential, and you should think that even if you have naked singularity which arises from smooth data, then Christodoulou's proof requires perturbing it into a very low regularity class of solutions, and I'll say more about this. Okay, so then moving on to what's known in 2+1 dimensions. Well, basically rigorously, this has not been studied at all, so nothing is really known. But the results that I'll tell you about answer some of these questions. So first, regarding the construction of examples which are on the threshold, there are, the numerical results in this case are due to Pretorius and Choptuik in 2000. And again, I'll talk about this work more. But in an upcoming work with Igor Rodnyansky, we're constructing, the first basically rigorous examples of naked singularities which are on the threshold, right? And these are, the first example of this, well, for this model, but also is the first, instance for any models where, you can construct this rigorously. Okay, and then how about the question of weak cosmic censorship? So I'll also talk about that today. So we're going to prove the weak cosmic censorship conjecture for the circularly symmetric Einstein scalar field system with a negative cosmological constant. And I just want to emphasize that this proof actually works in a topology of arbitrary smoothness. So there's no need to restrict to low regularity or any of that. You can just work in a topology that is very nice and regular. Okay, so these are the two results that I'll talk about today. And I want to start by talking about the weak cosmic censorship. But for that, I need to just introduce a bit of notation. And I'll have to tell you a bit about the moduli space of initial data. So I'm going to denote by this frac M the moduli space of CK asymptotically ADS characteristic data. And I'm not going to define this precisely for you, but just keep in mind that K is any integer that's at least 2. And okay, so you can you can give a structure of a metric space. So in particular, you can have a topology on this moduli space. And now, basically, what I told you here that all the solutions that arise in the gravitational collapse have one of these Penrose diagrams will actually give the composition of the moduli space as follows. So I'm going to define each of these components for you. So first of all, I'm going to denote by M space like black. So I'm going to denote by M space like black. This is the subset of initial data that in evolution forms a black hole spacetime with a space like only singularity. Okay, and then the next one is M locally naked black, which again is the subset of initial data that in evolution forms a black hole spacetime with a locally naked singularity. So with a null piece here. Then of course M naked is again subset of initial data that in evolution forms naked singularity spacetimes. And finally, M non-collapse is the subset of initial data that forms non-collapsing spacetimes. Okay, so this is the composition of the moduli space of initial data that you get. And moreover, it's actually convenient to sort of have some further notation. So I already told you that these two are the black hole spacetimes that can arise in this model. So I'm going to denote the union of these as M black. So this is the initial data that leads to black hole spacetimes. And then finally, I'm going to denote the union of these two, M locally naked. So again, this is the initial data that leads to locally naked singularity spacetimes. And so keep in mind that this can be black hole spacetimes. So then again, locally naked just means that you have a null piece over here. So this can either be black hole spacetimes or naked singularities. Again, of course, have a null piece. Okay, so this is the notation that I need. It's done. And with this notation, now I can actually state the main result. So this is weak cosmic censorship. For any k that's at least 2, the maximal development of generic circularly symmetric CK asymptotically ADS characteristic data does not contain naked singularities. Okay, so that's the statement of weak cosmic censorship, but let me be more precise. And so I'm going to define this set, which I'll call M generic, which is, so this is just the union of M black, so there's the black hole spacetimes. This is black hole spacetimes and the interior of M non. Okay, so this is what I'll call M generic. And so we prove that this is open and dense in M. So my notion of genericity is that this set is open and dense in the moduli space of initial data. Okay, and then the statement is basically captured by these inclusions. So we show that M naked is, let me maybe be here, sorry. So we show that M naked is contained in the closure of M black minus M black, which is further contained in the complement of M generic. So the first inclusion says that naked singularity spacetimes are unstable to black hole formation. right? So M naked is contained in the closure of M black. And then the second inclusion says that naked singularity spacetimes are non-generic because, again, M naked is in the complement of M generic, and M generic is an open and dense subset of M. Okay? And furthermore, this is also very important, we prove this inclusion. So M locally naked is in the closure of M space like black minus M space like black. So this is the statement that locally naked singularity spacetimes, so these two, are unstable to the formation of space-like only singularities. Okay, so again, so basically what I'm saying is that these two pictures are unstable to that. Okay? So this is the statement of the main theorem, again, in quite some detail. Any questions? Okay. So now, before I start talking about the proof, let me compare this with the statement.
I missed that. So you seem to be saying space like a generic situation.
So it's not.
Space like singularities inside a black hole.
Yeah. So it's not. You know, it's not. Basically, all locally naked things are unstable to M space-like, but I'm not claiming that M space-like is generic itself because I'm not claiming that M space-like black, for example, is open and dense. I cannot.
So you're saying anything locally naked can be perturbed to a pure space.
Yes, exactly, exactly. So that's that, but that's somehow the essential step is that all of these are unstable to becoming space-like only. But the generic, strictly speaking, what I showed that is generic is either a black hole spacetime or, you know, non-collapsing spacetimes. Okay. Yeah. So let me compare the statement of these with the statement of Christodoulou's recursive censorship in 3+1 dimensions. So first, so of course, that's, you know, for the different model in spherical symmetry, Einstein scalar field. So first of all, we use different notions of genericity. So in our case, generic means open and dense, whereas Christodoulou's notion of genericity, he shows that naked singularity spacetimes have positive codimension in the moduli space of data. So this notion of genericity that I'm using is a bit weaker. And you know, you should think that this has to do with the fact that when you have a negative cosmological constant, there's a boundary at infinity, and I have boundary conditions. So this well, will place some restrictions on how I'm doing my initial data perturbations. But more importantly, I want to emphasize the difference in terms of the regularity that I have on the moduli space. So in our case, topology is given by CK for any K greater, which is at least 2. So this is, you know, can be however smooth. Whereas in Christodoulou's case, as I said, you know, this result is for low regularity initial, you know, for low regularity space of solutions. And in particular, what he works with is the AC space. These are absolutely continuous functions, which of course can be quite rough. Whereas, you know, in our case, again, there's no restriction on this regularity. You can work in any CK. Okay, so these are the differences. And now I'll start talking about the proof. So the overall, yeah, let me just stay here because my pointer doesn't work very well. So the overall strategy of the proof, again, is due to Christodoulou, and I'll try to explain sort of what are the difference, but also similarities to his work. So there are two ingredients that are very important for the proof. And the first one of them is what I call the presence of a mass gap. So I'm defining the Hawking mass as follows. So my mass is minus g of grad r minus lambda r squared plus 1. Okay, so you might call, well, because of this term, some people might call this renormalized Hawking mass. And also, let me make a comment for the people who are more familiar with the physics literature. So I'm adding a 1 from the convention in the physics literature because I want my Hawking mass to be 0 in ADS spacetime and also to always be non-negative. Okay, so that's the convention that I'm using. In ADS spacetime, my mass is 0. Okay, and the Hawking mass has good monotonicity properties. And very importantly for us, we showed that to form singularities, you need mass at least 1. So in ADS spacetime, mass is 0, but to form singularities, you need mass at least 1. And this is what I call a mass gap. So the result that we prove is that if you have a disk bounded by a circle with Hawking mass less than 1, then no singularities form in the domain of dependence of this disk. Okay, so this is what I call the mass gap result. And there's two essential consequences of this result that I'll mention next. So the most important use of this result is that this gives us a description of first singularities at the center. Okay, so here's what I mean by this. Maybe let me draw it again. So let's say I have a first singularity at the center. So this is B gamma. Then what I claim is that the mass on the backwards light cone of this singularity must go to 1 from above. Okay? So the mass at the center is 0, but for any singularity, the mass must go to 1. Okay? And this, you should think, it really applies for all of these examples where you have a first singularity at the center, you always get the mass goes to 1 here. So this will be the essential description of first singularities that we get from the mass gap. And there's another corollary which is sort of interesting. It doesn't actually play any role in the proof, but this in particular settles the conjecture of Bizon and Yalmuzna. So what you get is that actually small perturbations of ADS spacetime are non-collapsing. So ADS spacetime looks like that, but it has mass 0. So of course, small perturbations, you will have mass still less than 1, so they will be non-collapsing. But this is a very sort of striking difference in 2+1 dimensions compared to the 3+1 case, where we know that ADS spacetime is unstable to black hole formation. Okay, so that's something that's also interesting. Okay, so the second ingredient is what's called the formation of trap surface criterion. So this is very much analogous to the result of Christodoulou in 3+1 dimensions. And the idea is to show that if you have a region with too much energy, then compared to the size of the region, then in evolution, you will form trap surfaces. So let me be more precise. And okay, before reading the statement, let's look at the setup that I have here. So I have an outgoing cone C0 plus, and my ingoing cone C0 minus ends with a first singularity at the center. And I have another cone C1 minus, which is to the out, so it's to the exterior of C0 minus. Okay, and I'm going to look at these spheres. So I'm going to look at these two spheres, which are the intersection of C0 plus with C0 minus and C1 minus. So these are the two spheres where I'm evaluating everything. So first, I denote by delta naught. This is a dimensionless quantity which measures the size of this annular region. Okay, so where I put my cursor, that's the annular region, and delta naught measures the size of this region. Yes.
Sorry to interrupt this slide, but just about the ADS,
oh, yes.
Are you able to say something about like when passing?
Well, so it's complicated, right? So actually, I think the expectation based on the numerics that they have, so they conjecture that it is non-collapsing, and that's true. But I think the expectation is not that it asymptotes back to ADS, but that okay, it exhibits weak turbulence or something like that. So that's, but yeah, okay, that of course I don't prove, but sort of softly you can at least get it. It's non-collapsing. Yeah. Okay. Sorry. So where was I? Yeah. So I was saying that delta naught measures the size of this annular region, and then eta naught is, so this is defined as, again, the difference of mass in this annular region divided by lambda r squared. So first note that this is also dimensionless quantity, because in two dimensions, mass is dimensionless. Lambda has units of 1 over length squared. So this lambda r squared is also dimensionless. And eta is a measurement of the energy contained in this annular region, because if you look at the usual propagation equation for the mass, that sees derivative of scalar field squared. So this really measures the energy. So what the result then says is that if eta naught is greater than delta and greater than 0, so too much energy in this region, then you get trap surfaces in the future on C1 minus. So you see too much energy down here. That means that at some point you'll start getting trap surfaces. Okay, so this will be the second essential ingredient that we're going to use. Okay, so now let me start talking about the proof of the main theorem. And somehow the main step is showing that was the second ingredient that I wrote, and it's showing that locally naked singularity spacetimes are unstable to the formation of space-like only singularities. Okay, so somehow once you do that, then you can prove that naked singularities are non-generic and so on. And let me also emphasize that the key point is showing that these are actually unstable to forming trap surfaces arbitrarily close to B gamma, because basically once you have an apparent horizon that goes into B gamma, then you know that your singularity is space-like only. Okay, so that's going to be what we're trying to show. And so I'm going to fix mg phi to be the evolution of a data set D, which is in locally naked. So maybe I'll have that drawn here. Okay. So this is the picture that I fixed, and I want to show that this can be perturbed to form trap surfaces arbitrarily close to B gamma, and that will mean that this is unstable to forming the space like only singularity. Okay, so I'm also going to choose, I'm going to set my double null coordinates once and for all. So this is a very standard sort of convention. So I want C0 minus to be given by V equals 0. And here I'll have the DUR is minus 1/2. And then I want my outgoing cone to be given to have DVR to be 1/2. And in this case, okay, so then my first singularity at the center will always be at 0, 0. Okay, so this is how I'm fixing my coordinates from now on. Okay, so a key role in proving this result is the blue shift. Okay, so this is, again, something that I'm sure you've heard of, but I want to show you how it arises because it's very natural. And for this, I'm going to look at this theta, which is a renormalized outgoing derivative of the scalar field. So square root r is very natural in 2+1 dimensions, and then this is just dv phi divided by dvr. And the point is that the wave equation for phi and for r imply a du equation for theta. So in this equation, I have this first order term, which, okay, multiplies theta. And then the other terms I'm not writing because the point is that in the regime that I'm working in, this will always lead to error terms. So somehow the key point will be that really the most important things happen exactly due to this term. And then the blue shift is just the integrating factor in this equation. Okay? So it's that simple. And I'm only writing this quantity, I guess, on C0 minus, but yeah, it's defined here as the integrating factor. So then what the mass gap, I mean, this is basically immediate computation. What the mass gap theorem implies is that actually the blue shift is unbounded on C0 minus, and moreover, I have a quantitative lower bound for the blue shift, so it's bounded from below by 2 times log u, right? So this now applies for any first singularity again, for those two, but also for in the black hole case, you always get that the blue shift is unbounded and it's bounded from below by 2 times log. Okay? So this will be a key ingredient that I'm going to use. Oh, sorry, I already skipped. Yeah. So this will be a key ingredient that we're going to use. Okay. So now, in order to show that these things are unstable, I first need to actually prove some, to have some quantitative control of general such solutions. Okay. So this is what I'm explaining now, and the point is that I'm actually going to prove some quantitative estimates again for general locally naked singularity spacetimes, and I'll do this in a region that I draw here as P. So this region is exterior to the cone C0 minus. And you should think that this region depends on the strength of the blue shift on this backward cone C0 minus. So somehow the stronger the blue shift is, the smaller this region in which I can have some quantitative control is as well. Okay, and in order to do this, there's 2 key points. So first of all, the fact that the blue shift is unbounded, so there's something that blows up and grows, and this allows me to then express sort of everything using this quantity that grows. And the second point is a bit more subtle, and this idea is very much goes back to Christodoulou, is to use the contrapositive of the formation of trap surface criterion to get L2 control for theta. So if I go back just a bit more, here, you see that eta naught, again, is a measurement of the energy. So this basically sees the L2 norm of theta. And if eta naught is greater than delta, I have trap surfaces, but that tells me that if there are no trap surfaces, then I actually get a bound on eta naught. So that's a bound on the L2 norm of theta. So, and now what I'm using is the fact that nowhere here do I form trap surfaces. So then everywhere in P, I will have L2 control for the on theta. Okay, so I basically, it's not just on theta, but everywhere in P, I have this control. Okay, so that's the second very important ingredient. So now I can tell you what the blue shift instability is. So here's the perturbation that I consider. So I take any n which is greater than k plus 1 and any lambda which is non-zero, and I do an initial data perturbation which is supported for v greater than 0. So I always leave, I never touch this interior region. I always do something that's supported in the exterior. So my perturbation simply leaves r unchanged. And for theta, I just add, so I take the old theta and I add lambda v to the n. So again, is that simple? And the key point, though, is that because I can do this for n greater than k plus 1, if theta is in ck, then the perturbation will also be in ck. So I don't need to restrict here. If I had to restrict to some finite n, some fixed n, which independent of k, then I would not be able to prove things for arbitrary smoothness, and You could also get issues for low regularity and so on like that. But here, the point is that I can really do this for any smooth test. Okay, and this is, and of course, the higher the n, the harder it is to do this. But okay, you can do it. Okay, so this is the perturbation that I do. And now I want to show that once I did this perturbation, I want to show that I'm going to get trapped surfaces arbitrarily close to B gamma. But of course, so there's some kind of instability. But of course, in order to prove instability, I also need some kind of stability. So first, I need to actually prove quantitative estimates in a region. So this region I'm going to denote by P lambda. And again, this region depends on the strength of the blue shift, but moreover also depends on lambda and n. And you should really think that this region is much, much thinner than the previous region P in which I had control. Okay, so let me tell you a bit how this works. So again, the key equation is looking at the D equation for theta. And now I'm looking at this equation for the difference of theta lambda and theta. And I'm not writing these terms here because I'll prove that they are error terms, and all the work goes into showing that whatever else is in this equation will not contribute. It will only be an error term. So what we prove is actually that the main contribution in theta lambda minus theta comes from the blue shift. So there's the integrating factor, which multiplies the initial data perturbation. But I'm the one who chose the initial data perturbation. So the initial data perturbation is just lambda v to the n. Okay. So, and also keep in mind that the blue shift grows. So that means that theta lambda minus theta grows as well. If I measure this in L2, this thing is growing because of the blue shift. Okay, but I also said that if I just look at the locally naked singularity spacetime, this has no trapped surfaces. So I have L2 bounds or L2 control on theta everywhere. So if I combine these two things, this basically tells me that once I get very close to B gamma, I have lower bounds for the L2 norm of theta lambda. Okay? So this now is really, this is what you should call the blue shift instability, the fact that theta lambda in L2 gets really amplified by the blue shift as you get very, very close to the singularity. Okay, so that's what the blue shift does for you. And once you have this fact, you can basically show that you form trapped surfaces as follows. So I now consider a curve C lambda. So this curve, you have to choose it wisely, but basically it enters the region P lambda very close to B gamma, and it ends at B gamma. And on this curve, I'll be able to apply the formation of trapped surface criterion. So I take any sphere. So let's just take this sphere, for example. Yeah, I take any sphere on this curve, and I have lower bounds. So I have lower bounds on the L2 norm of theta lambda in this tiny, tiny region here. So this is an annular region, right? So those I have by the blue shift instability. So my blue shift instability took my perturbation, and by the time I got here, it made it very, very large. Okay, but actually having lower bounds on theta lambda, then it will imply lower bounds on the eta that I defined before. So eta was some kind of measurement of the energy contained in an annular region, and precisely blue shift instability will tell me that this quantity is large as well. And you can choose everything in a way that this quantity will be larger than the size of the region. So again, the idea is that by the time I get here, the blue shift instability made my eta larger than the size of this tiny, tiny region. Yes.
So he's trying to compare with the 3+1 case. So what exactly about this, about your understanding of the blue shift allows you to take this like at so it's this.
So yeah, I'm not exactly sure how to answer that, because somehow it's just the different scalings that happen in the problem. In one case seem to limit your n, and in the other case seem to allow for n to be anything. But yeah, I don't know how to be more specific than that. And also it's a bit hard to compare, right? Because in reality, in this proof, I'm following very closely exactly how the perturbation enters the regime where I can now apply the formation of trapped surface criterion. So I understand exactly how my perturbation gets there. Whereas in Christodoulou's case, at all time, this is actually a proof about what this spacetime needs to satisfy in order to not have trapped surfaces. So it's more of proving necessary conditions that, you could say in some sense that his proof is a proof by contradiction. So you don't really understand how you enter the regime. You just know that, okay, you form trapped surface somehow. So it's a bit harder. You can't just look at the two things and compare them, I think. Yeah.
So for Christodoulou's case, it means that eta to be larger than delta log 1 or delta. And here you cannot log 1 or delta. And in all these regularity argument, there clearly is not one of delta. Because of here, they don't have that, so maybe they allow you to make this very large.
I personally, yeah, I don't know. I'm not sure if that log is that fundamental. For example, maybe the log could have, I could have had the log there here too, and still. So if anything, okay, maybe a way of, well, I'm derailing, so I'm sorry, but maybe something that I think plays an important role, that kind of, which is what I mean by the scaling is this problem, is that in Christodoulos case, the energy content is measured as a difference in mass divided by R. That's what you do have to do to get something dimensionless. And you might naively think, well, in 2 + 1 dimensions, I just go 1 dimension lower, so that should be just the difference in mass. However, you see here, the actual quantity, which is still dimensionless, is lambda R squared. But having R here, this makes eta much, much bigger in general. So it almost makes trap surfaces somehow easier to form, because going lower in dimension should make my R go away, but somehow I'm gaining an extra R. And that's, again, in some sense, you could say that, oh, well, that probably makes trap surfaces maybe easier to form. And then I can form them with small perturbations which are smoother, which somehow makes the perturbations smaller. So that this could be an interpretation, but it's very hard to compare, I guess, different scales. But I would think if this was not, if lambda R squared was not there, good luck. I don't think there's no way you can do it with that. Yeah, so I think it's really from there where it comes from. Okay, so let's see where we were. Yeah, so basically what I said is that I'm showing that here I have a lot of energy compared to the size of the region. So now I'm just applying the formation of trap surface criterion, which tells me that on the ingoing cone passing through this sphere, in the future, I will start forming trap surfaces, right? So again, at no point do I get trap surfaces in the region where I control things. That will be very hard to do. All I'm showing is that I entered the regime in which I apply this formation of trap surface criterion, and my trap surfaces should really think form out here. And of course, I can now prove, I did this for any sphere. So as this gets closer to B gamma, I get trap surfaces closer and closer to B gamma. So that means that I get a space-like singularity at the end of the day. Okay, so this is sort of the main points of the proof of cosmic censorship. Okay, so now in the remaining time, let me go back to what result I promised in 2 + 1 dimensions. So okay, we're done talking about cosmic censorship. So now I want to talk about constructing examples of naked singularity spacetimes which lie on the threshold of non-collapsing and forming black holes. Okay, so this will be a joint work with Igor Rodniansky. Okay, so here's the result that we have, and I'll call this local critical collapse, and I'll explain to you what I mean by local. So again, this is the upcoming work with Igor Rodniansky. So we consider a finite outgoing cone C0 plus. So this is a cone of constant U, but you see my R will be bounded by R naught. So it doesn't go all the way to infinity because we didn't want to have to deal with the boundary in this case, and we are sticking with everything sort of locally. So this is really going to be a local understanding of singularities. Okay, and what we do is we construct a 2-parameter family of C3 characteristic data labeled by dq lambda, where q is any integer which is at least 4, and lambda, okay, is something small. And here's what this family satisfies. So when lambda is less than 0, I'll show pictures very soon in case you cannot follow text. So when lambda is less than 0, the development of the data does not form singularities. So you're non-collapsing when lambda is less than 0. When lambda is equal to 0, the development of the data is a locally naked singularity spacetimes and contains no trap surfaces. Moreover, exactly when lambda is 0 and q is 4, these are precisely the numerical examples of Pretorius and Job-Tuig from 2000. So in particular, we give a rigorous construction of their examples, but somehow very interesting, we actually construct an infinite family. So, for all q, which is r at least 4, we construct such 1-parameter families. Okay, and then finally, when lambda is greater than 0, the development of the data contains trap surfaces. So you should really think that these lambda, so for lambda equals 0, this is the threshold behavior that we have, which lies, again, on the threshold of not collapsing, that's for lambda less than 0, and forming trap surfaces, that's for lambda greater than 0. And moreover, so you see, this data, as I said, arises, this is C3 data, but okay, there is no real restriction on the data. We prove C3, presumably we would have done C4 and so on. And this is really, the numerics, of course, of Pretorius Job-Tuig say that this should be smooth, and the expectation is indeed that this should be smooth, but also just by showing C3, we're basically saying that there's no low regularity issue here. These are much, much smoother than the previous examples that have been constructed for scalar field models. Okay, so now let me show you a picture of this result to make things more clear. So when lambda is less than 0, in the domain of dependence, I get no singularities. So I just look like this. When lambda is equal to 0, I get a locally naked, I get a singularity at big gamma, but there's no trap surfaces. I only have this null boundary arising out of it. And then when lambda is greater than 0, I have a space-like only singularity. Okay. So, sorry?
Is there a black hole?
So the point is that, a black hole is obviously globally defined, and everything we do here is locally, so we are not going all the way to the boundary.
Yeah,
so,
okay, but is there a trap surface before?
yeah, so, sorry. So before a space like the space-like singularity, you necessarily must have a black hole. So trap surfaces. So the apparent horizon, whenever you have a space-like singularity, the apparent horizon must go into there. Yeah, but indeed, also just to emphasize that again, you see, I'm not going all the way to infinity, so I cannot, this is all local. Okay, so this is the result that we're proving. And also, very much unlike numerical relativity, we cannot sort of analytically start with something that is non-collapsing and a black hole and kind of interpolate to find this. This would be very, very hard to do analytically. So actually, our strategy is to start by constructing these, so the threshold behavior first, and then prove that this can be perturbed to get something non-collapsing, and this can be perturbed to get something that forms trap surfaces. In view of the cosmic censorship proof, somehow this step, there's other ways to do it, but at least this step you can, let's say, that I've already explained to you earlier. Okay, but somehow the part that I'll show you is how to perturb to get something non-collapsing, which that's somehow way more surprising. I think that you'd have a singularity and perturb it away. Okay, so first I'll talk about how to construct these examples. And again, as we heard earlier today, a very good idea when you want to construct some kind of singularity is to do something self-similar. The issue, though, is that because of the cosmological constant, there's no exact scaling in this problem, so I cannot just have a self-similar ansatz. And as a result, we'll actually end up constructing solutions which will have different approximate scalings in these three regions. So the first region will be a region which is close to the center gamma. The second region is a region that's close to the backward cone C0 minus, and the third region is the region exterior to C0 minus. And the solution will truly live on different scales in all of these regions. But now, precisely because you expect these two things to have different scalings, it's very hard to actually come up with data on C0 plus, because you would have to prescribe something that already sees all these behaviors. So instead, what we do is we start with data at the center. So we'll prescribe data precisely at the center, then evolve sideways from here, construct the whole solution, and only at the end infer what the initial data on C0 plus was. Okay, so somehow that's the strategy. And what do you put at the center, where this is very much inspired what they get in the numerical relativity results? So we put for phi just a constant times log. And the c is at this point, let's say, allowed to be anything between 0 and 1. This will be further restricted. But you see, with this data, we know for sure that big gamma is a first singularity at the center. The scalar field blows up. Okay, so then let me tell you, again, proving things by pictures, how to construct each of these regions. Okay, can I have maybe 5 more minutes? That's okay. Okay. So first, the first region, this is the region near the center. The point is that here, the solution is approximately self-similar. And it's really, the point is that near the center, the cosmological constant is somehow lower order because it comes multiplied by r all the time. R is close to 0. So you can use that as an approximation. And then, of course, you have to correct this to a true solution. You have to do energy estimates and something that's a lot more involved. But somehow, a top order, the solution will be given to you by something that's approximately self-similar. And then you move on to the second region. And now in this region, I'm looking at the solution on this intermediate curve that separates the region 1 and 2. And actually, the solution in region 2 will be given by approximately solving ODEs in the DU direction. So I start with data on this intermediate curve. And again, to construct, again, an approximation, I propagate in the DU direction backwards. And of course, then this you have to do energy estimates and so on to construct a true solution. But that's how you get your solution in the second region. And now something very interesting happens is that to actually be regular across C0 minus, up to this point, my C, so I had a constant which was anything between 0 and 1. But now for regularity purposes, you have to restrict to a discrete set of values. So precisely what we get is that C squared has to be 2q minus 1 divided by 2q, where q is an integer that's at least 4. Okay? You need that for regularity. And this is why we construct sort of this q will be a discrete thing. And it's also very interesting that the proof works only when Q is at least 4. And when Q is precisely 4, we get exactly the examples of, Pretorius job 2. So that's somehow the lowest Q for which your proof works, gives you those numerical examples, but you get infinitely many such examples because Q can be anything. Okay, and then finally, you have to do construct the region 3, where you start with the data on C0 minus, and also you prescribe what behavior you expect on having this null boundary to construct your solution here. Okay, so now that we constructed the solution, the question is, how do I perturb this? And I'll show you how to perturb them to non-collapse. Okay, so somehow that's maybe the more surprising part. And one thing that's very hard to do is to start with initial data and perturb at the level of initial data to get something that doesn't collapse, precisely because what I explained in the proof of cosmic censorship is that you have this infinite blue shift, and yeah, I don't know how to do a perturbation that doesn't activate this blue shift. So then what you do instead is you get very, very close to your singularity. So I take C lambda, and you should think this C lambda, as lambda goes to 0, this gets close, this literally converges to big P0. So this region is very, very small, and I want to make my perturbation here. And the perturbation that I make here is again inspired by what people do in numerics. So I just take my scalar field and I vary its amplitude linearly, as 1 plus lambda times the whole scalar field. Of course, I have to do something for R and the labs. That's way more complicated. Let me not get into that, but let's pretend this is the perturbation that I make. And now my data is only given here. And to actually construct a 1-parameter data at the level of the initial data cone, I have to evolve all the way back to C0 plus. And this, since lambda is very small, I basically have to evolve for time 1. So I need some kind of stability. But we just said that if forward you had an infinite blue shift, that means that going backwards, I have redshift effect, which is a stabilizing mechanism. So that allows me to go back all the way to this initial cone. So now I have my solution constructed in this region. And why does this not collapse in the future? Well, basically, my perturbation, you see, is chosen when lambda is negative. This decreases the amplitude of the scalar field. But the mass measures the energy of the scalar field, so decreasing the amplitude actually decreases the mass. So you can actually construct everything in a way that when lambda is negative, the mass precisely on this sphere will be less than 1. So I'm decreasing the mass to drop just below 1. But once the mass drops below 1, I'm done because I don't have to do any more work because I have my mass gap theorem, which tells me that there's no way I can form singularities in the future and I'm non-collapsing. Okay, so somehow there's a point that, at the end of the day, I construct initial data here that, by the time it evolves to C lambda, the mass will be less than 1. And then, for sure, you're non-collapsing. Okay, so let me just have this picture up. And okay, I'll stop with that.